Welcome all to this 10th lecture of Principles of Statistics. I've received the second week feedback from you guys, and I've gathered maybe a couple of sort of main criticisms. So the first one is about my writing and the abbreviations. And I totally admit that my writing is certainly, there is room for improvement. And this is actually the reason why I'm writing in capital letters, because my handwriting is generally quite bad. And I've tried to improve this for years. So I shall carry on trying to improve it, but do be aware of the fact that I know about it. And this is the reason why I'm writing in capital letters. And now regarding the abbreviations, I'll try to abbreviate a bit less than this, than what I'm doing so far. But I was hoping that given that you have the recordings, then it shouldn't be too hard to, as you're listening to it for the first time, just annotate whatever feels unclear to you. And as a consequence, some of you said that you're using Quentin's Berthet's notes, so the PDF notes from a previous lecture, which are unofficial. So let me emphasize that again, because there are, I know that many of the contents are very similar, but you should be careful with the technical details because there are differences. Yeah. Okay. So just be aware of it if you want to use Quentin's lecture notes. And there was a second conclusion that I got, which is, let me just look at the feedback again. Oh yes. So there is something about me not being too clear about what is, sort of examinable or not, or what is important for the course or not. So I guess, and I also got another email about this in the past. So let me maybe clarify that indeed I do sort of like to give, a general overview of things and maybe sort of explain a bit in detail some technical details that may not be totally relevant for the course. But I think, to give you two ideas of, in terms at a practical level for exams, one is, the recommendation that I got the first time I joined the department is that, for lecturing, the schedules are the minimum, and for examining the schedules are the maximum. Yeah. So in line with that, the second thing is, do take a look at past papers, and I'm not going to change, the style of the questions themselves. So, I hope that sort of gives you an idea of how, the kind of questions I would be using. So, of course, do weight, the last couple of years more than previous years, yeah, in terms of past papers. Okay, so I hope that clarifies things. So let's get started. So in the last lecture, I mentioned that we would finish the, today we would finish the inferential procedures arising from the asymptotic normality of MLE. And so we'll start now with hypothesis testing. And then in the second part of the lecture, we're going to start with Bayesian inference. Okay, so so lecture 10, and as I'm saying, let's just consider hypothesis testing. So, so let's then state what we wish to do. So consider, sorry, I said I would try. So consider a hypothesis testing. And I think that I can shorten, so I will just use some of the, shortenings that I've been using, and those, will be throughout the course, but it's through the some words maybe I've just shortened once or twice, and that's maybe a bit unfair. So yeah, so consider a hypothesis testing problem as follows. So H0 is the hypothesis that, the data generating distribution, its parameter is in some capital theta naught, and then the alternative is just simply that that is not in that subset of the capital theta. Okay, and as I just said, well, this capital theta is a subset for some, if you like. Guy that isn't this guy, which is in RP still. Yeah. Okay. So what do we wish to do? Well, we wish to find so we wish to find a test, right? So this is a decision rule. So we'll go into details of what exactly is a decision rule later on in the course, but just to introduce the terminology. So decision rule psi n such that so the important thing is, so there are two things, I guess. So if it takes the value 0, then we accept H naught. And if psi n equals 1, then reject H naught, if you like, in favor of H1. And then the second thing that we wish to do is to control the errors. Okay, so this is what is called the two errors are the type 1 and 2 errors, okay, which are given by the following. So this would be the probability and the theta of rejecting H naught, okay, and this is just simply given by the expectation of this psi n. And then the important thing is that this theta is in the capital theta naught. Okay, so if H naught, so what this is saying is if H naught is is true, then what is the probability of making a mistake? Yeah, so having type 1 error in that case. Okay, and then the second, so the type 2 error is the probability of accepting H naught when actually H naught is not true, right? So then this is now this quantity, so 1 minus psi n, and this is when theta is not in theta naught, right? So that corresponds to H1, right? Okay, so we can introduce a general recipe to have a test or a decision rule, sort of for which we can have these two desirable sort of analysis. So then let me say, so a general, let's maybe say, so the so-called likelihood that I will keep on shortening, so likelihood ratio test statistic is a general recipe for these purposes. Okay, and this is defined as follows. So we call it this capital lambda of the capital theta and capital theta naught. And this is defined as 2 times the logarithm of the supremum over the first argument of precisely the likelihood. Okay, so in this case, I'm assuming already IIDness. Okay, so xi theta, and then the supremum over the second argument of the likelihood. Okay, right, and I guess this can be, okay, so that's the definition, and this is clearly going to be equal to the following, so 2 times log. So if we look for the supremum over the whole parameter space, then really what we have is that we are evaluating the likelihood at the MLE, right? And so then we have that the numerator is simply given by the MLE, and then the other one is the denominator is given by, if you like, the MLE for the restricted space. Okay, so where theta MLE naught is the MLE for, as I was saying, the restricted model. Okay, so now we can introduce a theorem. So theorem 6, and this is not for the general setting that we take in here, in which we consider a general subset of the capital theta, but a more specific choice. But this is an important theorem that we should be covering. So this is Wilks theorem. Which states the following. So assume that we have a statistical model, okay, satisfying the assumptions of asymptotic normality. This is A1, A2, and B, and that we are testing for capital theta naught to be equal to some theta naught. Okay, so this is a single element subset of the capital theta. Yes. So this is, of course, for some theta naught fixed. Yeah. Then, what does the theorem state? So we have that. So we have that under H naught. Okay, so really, when the data is generated by the distribution, P theta naught, the likelihood ratio test statistic is going to converge in distribution to a chi-squared distribution on P degrees of freedom. Okay. So I will make a few remarks about this theorem, but first let's prove it. And even before proving it, it's just occurring to me that I should also thank, first of all, I should thank everyone for the feedback, and then also thank for, the more positive feedback that I also got, which is encouraging. So yes, thank you all. I mean, I do like any ideas of how to improve, and then of course I also like it when people say that they like what I'm doing. Okay, so proof. So let's work. I'm going to, so the proof ideas, I'm not going to go in so much detail as I did for the asymptotic normality of the MLE, but some of the ideas are just the same. So let me state that we work on events, sets of events, okay, sets. Okay, so I will try to write better. On sets of events, set of events where we get that the theta n is in the interior of the parameter space. Okay, so remember these ENs, we have a similar idea to that. So just as in the other proof. So we're working on these sets which have asymptotically probability 1. Yeah. Okay, so then what do we have? Well, if we take this guy, okay, and write it out, then we see that, of course, what we get here, if you look at the second expression that is now on the top, what we have really is just 2 times the log likelihood at the MLE, and then the sort of equivalent quantity in the denominator. So we have ln at the MLE minus 2 times ln at theta naught. Yes, and that's because the restricted MLE, when the capital theta naught is just theta naught, lowercase theta naught, then of course it's just the evaluation at theta naught. Yeah. Okay. So then let's do Taylor here, and we're going to do Taylor of this guy around this guy. Okay, so we're sort of flipping the signs. So then this is going to be minus 2 times the derivative, the gradient of the ln of the log likelihood at, as I'm saying, the MLE. And this we transpose and multiply by the difference of these two. Yeah, that's right. Okay, so then what can we say? Well, we can write this out as follows. So we can write, sorry, no, I haven't really finished the Taylor expansion. So we need a second derivative. So then this is going to be given by theta naught minus theta MLE transpose, and then we have the Hessian, yeah, with respect to the theta of the ln, and now evaluated at a different value, okay, which we can call this theta n bar, and theta naught minus theta MLE. Okay, so, okay, and where, the important thing here is, so where this theta n bar is, or, consists of p intermediate values, okay, so mean values. So therefore, what I'm hiding a bit under the carpet is, the arguments, the type of arguments we had to control this AN bar matrix, okay, in the asymptotic normality of MLE proof. Yeah. So between mean values, okay, so let me write that out, values between theta naught and this theta MLE. Yeah. Okay, so now we can say that the right-hand side is, so we can write it as, I mean, note that the first term here, so this guy is going to be 0, right? And that's why we expanded the function around the MLE and not theta naught, right? Because we know that the MLE is the 0 of the gradient. Yeah. So then, so the right-hand side is going to be 0 plus, and we can sort of rewrite this quantity because the ln, remember, this is not normalized, and so we can divide it by n, and we can multiply everything by square root of n squared. Yep. So what am I saying? I'm just simply saying that we can write this guy and now change the order in both times the jn. Okay, so remember this guy at this intermediate, or these intermediate values, and the square root of n. Okay, theta MLE minus theta naught. Yeah. Okay, good. Okay, and then now this Jn we know how to control, and we know how to control the other guys, right? So this is looking better. So let's just rewrite this then as the square root of n of the MLE hat times theta naught transpose. And we know that this Jn at this intermediate value will, in theory, should go to, should convert to the Fisher information matrix. Yeah. So why not to add and subtract that Fisher information matrix at the true value, the theta naught, because we're working, of course, under the assumption of H naught. Remember that. So I mean, that's really what matters in terms of constructing a test. You always look at the distribution under the null hypothesis. Okay, and then whatever happens under the alternative is a secondary sort of analysis, yeah? Which is the analysis of power. But to construct a test, you just think of the null hypothesis. So that's really what you're testing for. Yeah. Okay. So we have then this square root of n and same quantity minus theta naught. Okay, so it's not going to fit, but we can add again, and I hope you don't mind if I write that just to speed up a bit. Sorry, that's wrong. Jn theta n bar minus this Fisher information matrix and square root of n times the same. Yeah. Okay. So as I was saying, we know properties about the terms here, different terms here. So recall then, the asymptotic normality of MLE. And so we know that this converges in distribution to a normal distribution that is centered and that it has covariance matrix given by the inverse Fisher information. So remember, this is the sort of asymptotic efficiency. And then the other thing we know from, from previous lecture is that this Jn at theta naught, yeah, okay. Okay, so let me just state this, recall this, and I guess fact. Yeah. So this is going to convert to, so in distribution again, to I theta naught, but actually we can say that it converges in probability as well. Yeah. So this converges in probability, and this is under the theta naught. This, okay, and I'm saying this is a fact because I think I must have stated the previous result about this sort of empirical Fisher information evaluated at a fixed theta rather than having a random guy. But then, of course, you sort of apply the same ideas that we had in the asymptotic normality of MLE, in which we had such a thing for the capital AN bar. And so really it's just the same type of reasoning. Yeah. Okay. So now furthermore, so you should be comfortable with these sort of arguments. Yeah. Just thinking about the feedback about what is important and what is not. Well, that those sort of arguments is arguments that are standard for the course. So this should be you should be familiar with them. Okay. So furthermore, this function here, or well, if you like, as a function of x. Okay. So I didn't do the mapping, but this function is continuous on Rp to R, and therefore we can apply the continuous mapping theorem. So by the continuous mapping theorem, we have that so this guy, will convert in distribution. So this guy's to the left-hand side from the whole chain of equalities. What we have therefore is that this second guy here is going to go to 0, and this first guy is going to go to simply, if we write Z transpose I theta naught Z, where, let me say, and writing Z as a normal distribution that is centered with this covariance, then we get that. And now if we write letting Zi, maybe Zj, be IID, with a normal distribution, standard normals, and this is for j equal 1 to p, then, if you think about this expression here, you can take the square root of the Fisher information matrix, because it is essentially a covariance matrix, and therefore, and actually you can prove it directly by the definition that it is definite, positive, semi-definite. Yeah. Okay. So then we can take the square root. So in fact, it will be definite, so positive definite, whenever the random variables are non-degenerate, and that's why you can invert it. But yeah, generally speaking, that's not necessary. So just the positive semi-definiteness is enough to take the square root, and so then you can absorb this through the Z and get independent standard normals, and get and write that the right hand side, so the guy I just underlined, equals the sum from j equal 1 to p of squares of IID standard normals. So then, of course, this is saying that this guy converts in distribution to chi-squared on p degrees of freedom. So that's the conclusion. Yeah. Okay, very well. So let's make some remarks. Okay, I think that should be clear. Okay, so the first one is, so we can take, so letting or writing, if you like, the following. So we have, sorry, let me define what I want to take psi n to be equal to the indicator of the set in which this capital lambda is greater or equal than psi alpha, and psi alpha was already defined in the previous lecture as the value for which, if you have a chi-squared on p degrees of freedom distribution, then is the value after which you have probability alpha. Okay. Okay. So letting this, we can control the type 1 error. Okay. Okay. At an asymptotic, I think asymptotic, you will allow me to always sort of shorten it. So asymptotic level or confidence level significance. Well, okay, asymptotic level 1 minus alpha. Okay, and that should be clear by the previous theorem, because the previous theorem is under H naught, and then we also worry about the type 2 errors. So that, first of all, by the way, the first objective of this being 1, of this being 0, and then accepting H naught, then is sort of, you should think about it that this makes sense. Okay, so and then by the Neyman, so the Neyman-Pearson lemma. Just close. Okay, so the Neyman-Pearson lemma, we expect precisely. So we expect the power, we expect, the power. Okay, no, I don't like this phrasing. So we expect good power, where power is no more than 1 minus type 2 error. Okay, so I think you must have seen the Neyman-Pearson lemma last year in Statistics 1b, but it essentially tells you that that this likelihood ratio test statistic is optimal in the sense of, if you fix the type 1 error, which is what one does, right, with this asymptotic level of 1 minus alpha, then you're now worried about optimizing the type 2 error, or the power, which is 1 minus the other one. And so if you want the power to be as high as possible, so that the type 2 error is as low as possible. And so the Neyman-Pearson lemma will tell you that this test is optimal in that sense for testing for testing the null hypothesis of having some theta naught as the true parameter, so a single element versus another single element. Yeah, so it's not really what we're considering here, because here we're considering testing a single element versus the rest. Yeah, but still, this Neyman-Pearson lemma gives us at least some hope that this test is actually a good test in the sense that I mentioned. Okay, so second remark is that, so you should be now thinking, oh, actually, but we've already seen confidence sets, right? And a confidence set that was based on Wald statistic. And so you would be thinking, well, can we use that to derive a test? And of course we can. So we can also test the null hypothesis of theta being equal to theta naught versus H1 being that theta is not theta naught. Okay, so the complement, if you like. And this is using this Wald statistic. So using, or if you like to start with, this is the MLE, not being in CN, so with CN as in the last lecture, which is essentially the same as testing the Wald statistic. Okay, so this would be MLE, and this being larger or equal than the Xi alpha. Yeah. Okay, and that is this Xi alpha still has the same meaning of this quantile, and we can also, so another sort of general recipe for testing is the following. So this is what is called the score test statistic, which is given by square root of n, denominator, sorry, Sn, yeah, so that's the score. Okay, and this guy, sometimes, by the way, people take the square of this quantity. Yeah, you should be aware of that. And call it the same, I mean, of course. So this is going to go to that, okay? And this is always, of course, under H naught. Yeah? Okay, and so really, I mean, remember that this Wald statistic was going to converge to a chi-squared on p degrees of freedom, and if you look at this SN, or this sort of score test statistic. Oh, sorry, I didn't mean to say exactly the square as an equivalent form. So what you can take is essentially you can multiply this guy by the Fisher information matrix, and okay, so what I wish to say is that if you multiply this guy, or if you take the square of this guy, but multiply him by the inverse, by the, what would it be? Yes, by the inverse of the Fisher information, sort of in the middle, so you have these two vectors and the matrix, then that's also called the score test statistic. And if you think about it, then what you will get in that one is again a chi-squared distribution on p degrees of freedom. And so you'll be thinking, well, that's a bit of a coincidence that the three tests sort of have this asymptotic distribution under the null hypothesis. And so is there a relationship between them? And indeed there is. So it turns out that the three tests are asymptotically equivalent under H naught. Okay. Okay, so all right. Okay, so then the last remark is that when we have the setting that we started with in the lecture, which is that the dimension of the capital theta naught is not necessarily, it's just general, and less than p, so not necessarily 0, then we get that, and under H naught, we get that the likelihood ratio test statistic converges in distribution to chi-squared on p minus p naught degrees of freedom. Yeah. So as I just mentioned, what we were considering before is the case in which p naught is 0, and so of course we recover Wilks theorem. Okay. All right. So enough for the asymptotic normality of MLE and its inferential, so the resulting inferential procedures. So let's now go into Bayesian inference. Okay. So we start with some basic ideas, and including the prior and posterior distributions. So basic ideas, including the prior and posterior. Distributions. Okay, so we, again, as always, we consider a statistical model. F theta with some theta in this capital theta. Okay, so what does a Bayesian sort of begin with? So a Bayesian, if you like, a Bayesian statistician, or someone from the Bayesian philosophy, will interpret theta as some sort of state of nature, yeah? As a state of nature that is inherently, excuse me, I will pause, random. Yep. Okay, and this is, of course, if it is, if it is random, then we must have at least if we try to formalize it mathematically, then we must have a distribution that is sort of depicting this randomness. Yeah? So according to some distribution, and we can call this pi, sometimes lowercase pi, which is called the prior distribution. Okay, so the prior distribution. Okay, so once we elicit this prior distribution, once pi is elicited, so what it really is representing, right? So there is no way that we can. Okay, so what it's really representing, so it describes the Bayesians or their. So if we thinking of a single person, then we sort of, or it is describing the essentially the beliefs, right? And I will go into that in a sec, the beliefs. And this is, of course, about nature, yeah? About this state of nature. So what do I mean by this? Well, I mean, if we're trying to model nature, then after all, if we're choosing, distribution for a random quantity, then there will always be some sort of degree of belief, like a subjective belief that we need to elicit that distribution. Okay, and this is in contrast or in opposition to what a frequentist would sort of think of reality, because they will not consider theta as a random state of nature, but rather, the data is generated by a single parameter. Okay, I will talk about the difference between the two in more detail, but that I will do in the next lecture after defining the posterior and after defining everything, because I think it comes in a bit more naturally there. So let me, for now, just give you an example of, or just some example actually linking to hypothesis testing and the Bayesian, philosophy that sort of also ties together with this sort of interpretation of the state of nature. Okay, so let's consider different hypotheses. So consider hypothesis Hj consisting of being theta j, which is here. Okay, so what we're proposing as a hypothesis is that the data is given by some, the instantiation of the data of this random parameter is theta j for different j's. So, and this is about, of course, as I'm just saying, about a law of nature. Okay. And we have to elicit some prior distribution, so with prior beliefs. Pi j equal to p, and this would be some p that is not necessarily the ones that we've been using before, but it's just the probability of some sort of probability of this h j. Okay, so let now define then the distribution under such hypothesis. So we define fjx to be this probability of our random variable when the true hypothesis is the jth one. And this, I'm taking equality here, so really I'm thinking of PMFs, but the definition for PDFs is just it just requires cosmetic changes. So then this is this is really saying that if Hj is true, then Fj is precisely the distribution of nature, right? Okay, so this is distribution of the observations. Okay, so now let's use the so-called Bayes rule. So by Bayes rule, and I informally remind you of this. So this would be saying that A given B equals the probability of B given A times probability of A divided by probability of B. Yeah. Okay. So by Bayes rule, we have that if we observe x equal x, then the probability, once we have data, we can ask about what is the new probability, given our prior and our new observation, what are the new probabilities of these different hypotheses, and why am I moving like that? Well, I will tell you in a sec. It's just because of my own interpretation, I guess, of these quantities. And so then by Bayes' rule, we have this sum over k of fkx pi k, okay? And this is what is called, by the way, the posterior distribution, okay? And so the reason why I was moving like that is essentially because one should think of the posterior distribution as some sort of update of the prior distribution. Okay, so we have our prior beliefs as a Bayesian, and then we get data, and what we do is we update these in some sort of sequential fashion. Okay, and so I guess this sequential fashion, so sequential by which I just mean that if you get new data, then because we sort of assume IIDness, then we will get products of the previous quantity. So we sort of multiply by the new, or at least the numerator, yeah, because if you have seen Bayesian statistics, we always sort of think of the numerator only. So we look at the proportion, so we always look at the posterior as something proportional to the numerator, yeah. And so you basically, as you get new data sequentially, you can update this sort of prior, and it feels like there will be some wiggly sort of process here. I guess it's just my brain that is thinking about it that way. But yeah, so let me just maybe say, so this is an update. So I'm saying an update of the prior through the data, yeah, or after observing data. Okay, all right, good. So the last comment about this is the following, and it is that we can choose. Maybe let's go to the next line. So we can choose. If we're doing testing, then we can choose Hj over Hk. So what's the simplest thing that comes to mind? Well, if we have that, the ratio between the probability of the Hj given the data and the probability of the Xk given the data is greater than or equal to 1, right? And let me now write this out. Well, the denominators in both quantities will cancel out, and so we get simply this expression here, pi j, with this ratio here. Yeah. And so again, what we see here is, so now that we defined these guys as the posteriors, or the posterior, we can call this the posterior odds, okay? This is obviously the likelihood ratio, and this is the prior odds, right? Okay, so what we see again is this sort of update of, so again, update of prior, in this case odds, through data. Yeah. Okay. And I guess just to end this, let's just say that in particular, if we take, if we assign the same probabilities to the jth hypothesis and the kth hypothesis, then the Bayesian odds well, or maybe posterior odds. Yes, let's just say posterior odds. Odds reduced to the likelihood ratio, right? Okay, which is, by the way, purely data dependent, if you like, and I don't fully like this that I'm saying myself, but I guess what I want to say is that if you have this sort of agnostic prior in which you're not really eliciting anything different to any different hypothesis, then really it all depends on the data. Yeah? And it actually depends on the likelihood ratio, so it really sort of connects back to the likelihood ratio test statistic. Okay, and lastly, we have that, of course, in general, this is not the case, and the latter, or the posterior odds, the likelihood ratio, not the posterior odds, is weighted by the prior odds. Yeah? Okay. AE, our beliefs. Yeah. Okay, so we sort of include, not only what the data is telling us, but also our sort of subjectivity in this. Okay, so we'll in the next lecture we'll define the posterior, more generality, and we'll also talk about, I guess, a more frequentist understanding of the Bayesian methodology. Okay, right. I hope you enjoyed the lecture, and see you again soon.